Do you think they can see it?
Do we think they can see it?
No, you haven't showed this one.
Oh, yeah.
That would be a good start.
There'll be a little yellow color around them.
Wow. All I'm seeing in Zoom is Hannah. Here we go. This one over here. Share screen. By the end of the semester, we'll have this down and we're
Will
showing
we?
that one. No, because then it won't matter. Okay, got it. It's been live streamed. Can you guys see the presentation slides?
Now we can see it. Yeah.
Yep.
Oh, we can hear you too. So.
Yeah, I plugged them back in. No,
Oh,
I just
okay.
plugged in.
So today we're having one of our PhD students present their research as we require them to, which means they must present at least 2 of the 3 papers that must be completed before it counts for their PhD defense. They do not need to do all 3. 3 papers cannot fit in a 45-minute colloquium. Please don't do it. But you must do 2. So today we're very lucky that we have Carly. Carly Muir is going to present her research, which is looking at environmental change in Ethiopia, evaluating trends in social ecological systems through geospatial analyses, which sounds somewhat like Nick's from last week, who is online, I saw. Hey, Nick. Okay, take it away.
Okay.
Anyone who came in late? Anybody?
All right. Thank you, everyone, for coming. So as Jane said, title Environmental Change in Ethiopia, Evaluating Trends in Socio-Ecological Systems Through Geospatial Analysis. A good title for a geographer, I think. All right, before I jump into the research itself, I want to try to place it into our broad field of geography. So my research interests, after 10 years of being here from my undergrad till now, have landed in land system science. I think that this is a great place for a geographer to be because land is this nexus of environmental and human well-being. But of course, because I have a background in climate, I also tie in climate change and then some agriculture as well. Generally, I take a top-down approach or a big picture look to spatial analysis, examining the connections between changes in the landscape and the climate so that I can try to understand coupled natural human systems. In this talk, I'll give you guys some context up front about Ethiopia, since all of the 3 chapters take place in Ethiopia. I'll go over chapters 1 and 2 in detail, and as Jane warned, I do have chapter 3 up here, but it is just 2 slides, so I'll try to get through that quickly and then wrap up with the conclusion. All right, so Ethiopia, some context. Looking first at the environment of Ethiopia. Ethiopia is a fascinating place to study because it is so diverse. So looking at the biophysical characteristics, we see things like land cover, hydroclimatology, topography, and a lot of different agroecological zones. I'll look at each one of these in particular and describe the diversity. So first, looking at the land cover, we see a lot of savanna out in the east and to the west as well. We have our cultivated lands up in the highlands, so where a lot of the agriculture is. We have some bare soil in this very dry region or a far depression up in the north. And then our forest is really limited to the southwest. Ethiopia has had a lot of deforestation in the last half century. And so that's just where a lot of the forest has ended up. Moving on to this next figure. This is our hydroclimatology. This is showing us rainfall regimes and Ethiopia. So when I did my master's work in Ghana, I was working in a place with bimodal regimes. And moving into Ethiopia, you can see just how more complicated it is. So we have a single peak up in the north and towards the west. This happens in June, July, August. And then as we move down into the south and towards the east, there's a bimodal regime. We get a we get one peak matching that in June, July, August, and then there is another peak in March, April, May. When we get down into the south again, we have a bimodal regime, but the second peak is going to come in October, November, December. Of course, this is related to that movement of the ITCC moving across the tropics. So the topography is also really important when we're thinking about the environment of Ethiopia. And you can see here what that looks like. Of course, again, our highlands in the center of the country, and this is, sort of split down the middle with that Rift Valley. We have lowlands on either side of our highlands. And then, of course, again, RFR depression up in the north. This last map here is showing you agroecological zones. So this one in particular, I think, has 15 on there. But because of all of the differences in things like land cover, elevation, and rainfall, you can get as many as 33 agroecological zones in Ethiopia. So it is really a complicated place to study when you're looking at the environment. All right, so moving on then, because of course, some social components and human geography is important as well. First, I'll talk about population. So Ethiopia is the second most populated country in Africa, and a lot of this is concentrated near the highlands, where there's good agricultural land, where we saw all that cultivated land cover, and there's also less risk of vector-borne disease. This map down here is showing you the population density, so you can see Addis Ababa, the capital city, right in the middle of the country, and then a lot of the concentration around it, especially down to the south. Now, one thing to mention about the population is that approximately 79% of the population is still considered rural. You can see what that looks like down here with World Bank data. So this is sub-Saharan Africa, the percent of the population that is considered rural, and this is Ethiopia. So when we're doing research in Ethiopia, you do have to be aware of just how rural this population or this demographic is. And then moving down here to talk about the economy. So Ethiopia is also a really interesting place because of the economy. It was one of the fastest growing economies in Africa. This is no longer the case for 2021 because of the unrest that occurred there or is occurring there. And it was within the top 10 globally. I don't know if it's still there, but so an interesting place, certainly a lot of transition happening in this country. 72% of the population derives its livelihood from agriculture, not really a surprise when we know that so much of the population is rural, certainly though something to note. And if we look at the GDP, we can see 37% is coming from agriculture, so quite a bit. Again, not a surprise knowing that Ethiopia is sort of still in the beginning phases of its demographic transition. And of this 37%, we see 35% of that GDP, that agricultural GDP, coming from pastoralist activity. Just to point out that, we're talking about pastoralists as well as, solely agriculturalists. Okay, so last bit of context I want to give you guys before I get into the research is regarding land degradation. So land degradation is a major issue for Ethiopia. It's a big hindrance to economic growth. And we see that most people now derive their livelihoods from degraded land. As much as 85% of Ethiopia's land is degraded to some degree. And we see severe erosion, especially up in the northern highlands. And because money talks, I've put this statistic up here, land degradation in Ethiopia equates to about $4.3 billion a year in terms of losses. And so that's 22.5% of the GDP. All right, so it's a really big, land degradation is a really big problem for Ethiopia. Now, what's causing this degradation? Population pressure is one factor that comes up again and again. So we see increased rural population density in Ethiopia, and this is putting pressure on that land. It's forced marginal land into production, and it has also, this increasing population density has also decreased the farm size. So farmers have tried to adapt to these issues, but the adaptation strategies haven't necessarily been the most sustainable or environmentally friendly. This includes things like reducing the fallow season, and oftentimes this is done without supplementing that with the necessary inputs, so we just get a lot of nutrient mining out of the soils. We also see overgrazing being a problem. So overgrazing, again, a consequence of this loss of available land. And farmers have had to make decisions between using crop residues for things like soil fertility versus feeding it to their livestock. So a lot of different things going on here, but certainly population being a huge pressure for the land. All right, then. Moving into the research, and I'm just going to take a drink really quick. starting with paper one. So this work was published in Remote Sensing last year. The title, Vegetation Dynamics and Climatological Drivers in Ethiopia at the Turn of the Century. And this work is grounded in looking at global environmental change. And we know global environmental change is going to alter vegetation composition and health, which we can think of as our vegetation dynamics. And vegetation dynamics are crucial for functioning of Earth system, the functioning of Earth system, right? So our vegetation dynamics are influencing things like albedo, the carbon cycle, hydrologic cycles, biodiversity, among other things. So our vegetation dynamics are really important. And oftentimes we see vegetation dynamics as a marker of larger global environmental change. There's also this factor of climate change, which is really heightening the vulnerability of the current system. So threatening to sort of tip our system and change the dynamics. And sub-Saharan Africa comes up over and over again as a region that is really vulnerable to climate change and to larger global environmental change. And this is in part because we have a lot of dry lands in this region, right? So these dry lands are areas where our climate and our vegetation are intricately linked. And so in particular, in sub-Saharan Africa, we see climate change being a major threat because of this. This image down here is just to show you guys a broad overview of the system dynamics and the vegetation interacting with all the other subsystems within Earth's larger system. But I will get to the meat of this, which is the research question. So research question number one, what trends have been shown in vegetation dynamics across Ethiopia since the turn of the century? And research question number two, what is the relationship of vegetation change to climate? So this is still not well understood for Ethiopia. In some regions, such as South Africa, we see a pretty consistent trend. When it comes to Ethiopia, what we see is more of a mixed signal. Some regions browning, some regions greening. We also see inconsistent trends, again, across studies, so across our region, but also over time. So this is a non-stationary relationship between climate and vegetation, where we see changes in the relationship depending on the study period that you're looking at. In this analysis, I use two sources of data. The first is moderate resolution imaging spectrometer, or MODIS, to get NDVI from Terra vegetation indices. So using NDVI, this is going to give us a proxy of vegetation health or biomass. I'm sure most of you guys are familiar with NDVI, but just in case you're not, we can see it's going to be a matter of the reflectance and the different wavelengths and showing us that healthy versus unhealthy vegetation. The next source of data is the climate hazard groups. I used two different data sets from them. The first is what we call CHIRPS, their rainfall data set, their monthly rainfall total. And then I used their CHIRPS data set, which is their monthly maximum temperature. So this data is aggregated into seasons for years 2000 to 2016. We have March, April, May, our spring, June, July, August, summer, September, October, November as our fall, and then December, January, February. I'll point out that rainfall is lagged by 1 month. So our NDVI for March, April, May is connected or associated with February, March, April rainfall, of course, to allow for that time of the response. I also want to point out this graphic here. So I know some people take issue with CHIRPS. It was very convenient for me that Dinku AL 2018 published a paper that validated the CHIRPS rainfall data set over Ethiopia. So it was very, very convenient for me there. All right, in terms of the methods, I'm going to break this up into two parts. I'll first talk about persistence, which is getting at the first research question of what are the vegetation dynamics doing, and then I'll go into the climate, which involves panel data sets and regression. So the persistence metric shows spatial persistence of the landscape, showing the productivity on an interannual basis, looking at changes in NDVI, and it does so in a spatially explicit manner, which allows us to look at trends across the region. This has been utilized to highlight regions of vulnerability through the patterns of positive and negative vegetation persistence, or NDVI, over time. And this metric has been used for a variety of environmental studies, looking at things like ecosystem suitability, vegetation health, of course, and land cover stability. Now, the way that this metric is operating, it's basically showing us a cumulative direction of change over time compared or relative to a benchmark. So our benchmark or our baseline period is 2000 to 2004, where we take the mean NDVI for each season, and we then compare this to the rest of the time series, our 2005 to 2016. And with that comparison, we're basically doing a random walk statistic. So for each pixel, looking at the NDVI value in a given year, in a given season, if it's higher than the baseline, it's going to get a positive one. If it's lower than the baseline, it's going to get a negative one. You can see a nice image showing you that here. At the end, these are all added up, and the final score is our persistence value. So thanks to the work of Whalen et al. 2014, we know that with our sample size of 12, if we see a persistence value of plus or minus 8, that is significant change. So we can say that there was a significant number of years where NDVI was either higher or lower than the baseline than what would be expected. And the output, of course, looks something like this. This is for South Africa. I'll show you Ethiopia in a little while. But before I get into those results, I'm going to go over the methods for the spatial panel model. So looking at question number 2, what is this relationship between climate and NDVI or vegetation? And this question has been asked many, many times by many, many different people in many different regions. But in many cases, the methods used to answer this question are not necessarily the best methods. We see things like Pearson correlation, Kendall's tau, standard regression, but these methods don't allow for simultaneous consideration of spatial and temporal characteristics. And this is important when we're talking about vegetation dynamics. So we see, again, non-stationary relationships between these variables, which we want to capture with these longer time series rather than just looking at a cross-sectional data set that's just going to show us one point in time. We also see with these techniques, there's potential for violation of the assumption of independence, right? When we're looking at geospatial data, that is certainly something that spatial autocorrelation is something we should all be concerned about. And G and Peters point out that this is something that has been, I don't want to say ignored, but for lack of a better word, ignored by some people in the literature in remote sensing. So this work tries to sort of build on, a more robust analysis by using panel data models. And these have become more widely used in remote sensing, especially looking at land cover, again, because they're allowing us to look at a longer time series across a region with multiple observations. So the panel data set includes 3 variables. We have NDVI, rainfall, and temperature. And these variables were extracted for more than 1,900 points on an annual basis at pixels where there was either a significant increase or a significant decrease in persistence. And these 2 samples are separated. In this model, I also use time fixed effects. So our time fixed effects are controlling for things that might change from year to year, but are going to stay constant across all of the observations. So potentially things like policy implemented at the federal level. And then what I think is most interesting here is the location fixed effects, so using latitude and longitude for that. And this allows us to look at things or to factor in things that we're not observing as a variable in and of itself, but things that are going to be specific to a particular observation at a particular location, but they are not going to change over the course of the study. So things like soil type. With this data, I run 3 different models. One is just a standard OLS, not including spatial fixed effects. But then I get into the spatial model. So I start with a quasi-spatial model. So I call this a quasi-spatial model because it is factoring in space and spatial relationships by using the location fixed effects. But what the quasi-spatial model cannot do is necessarily account for the spillover effects, right? We know that if we're looking at one observation and it's raining here, that rainfall is not going to stay in that pixel. It's going to move to its neighbor and it's going to affect its NDVI there. And so the spatial Durbin panel data model allows us to account for this relationship. So you can get an idea of what this looks like here. And this was run in the XSMLE package instead. Alrighty, so getting into the results then, here are the results for the persistence, and then I'll go over the results for the regression. On a seasonal basis, what we see is that most of the seasons are showing a greater proportion of negative persistence, meaning that there's more land that NDVI is lower than that benchmark versus areas where it would be higher than that benchmark. And the only exception to this is June, July, August. I will say that this is potentially due to all of this cloud cover, which you see here in these gray and white areas. So, you know, potentially that's why we actually see more positive persistence there. I also want to point out the largest amount of change, which you know, you may have noticed right away by looking at this graph, which is December, January, February, our dry season in Ethiopia. So 28.9% of the pixels analyzed during this season showed cumulative declines compared to the baseline. And so obviously much larger than the other seasons there. Now, you know, we can think about it temporally, but we're geographers, right? So we're going to think about it spatially as well. So looking at the regional differences, there are a few interesting patterns that stick out. First is the north-south divide in September, October, November, which you can see here. Right about here, we see north of that, a lot of negative persistence. And then just to the south, we see a lot more positive persistence. And so my thought, and of course, this will take further investigation, but my thought is that this is probably a signature of changes to the second rainy season in southern Ethiopia, perhaps something to do with the movement of the ITCZ. There's also a very interesting and distinct negative trend in the Ethiopian plateau and the Afar depression during December, January, February, which you can see here. Of course, again, we had all that negative persistence, and so seeing it displayed spatially here, you can see, you know, cutting right adjacent to the Afar depression, there is a lot of decline in NDVI, so potentially picking up that degradation that is happening in that region. Okay. Moving on to the results of the spatial panel model. So there's the results show that there's a significant relationship between temperature and significant negative relationship between temperature and NDVI, and significant positive relationship between precipitation and NDVI. This was not necessarily surprising, but what was surprising, what was interesting, is the change in the relationship when you incorporate a spatial component to the model. So the relationship between rainfall and NDVI weakened when location fixed effects were included, and the relationship between temperature and NDVI becomes more severe when we include a spatial component. And this is likely due to biased estimation when no spatial variable is included in the model, and I'll talk about that on the next slide. But you can see what I'm talking about here. If we look at, this is our non-spatial model. Here's the results for pixels that had positive persistence, pixels that had negative persistence, our precipitation and our temperature. And you can see the beta values change when we include the location fixed effects in our quasi-spatial model. So again, our precipitation, the relationship weakening for precipitation in terms of beta values, and then the temperature, the relationship for temperature increasing. So when we then include running the spatial Durbin model and trying to include the spatial the spillover effects, we do get very similar beta values to what we got with our quasi-spatial model. But I will point out that the R-squared does decrease drastically. I believe this is due to the way that it's calculated in the XSMLE package. And I should have also pointed out here that when we go from our non-spatial model to our quasi-spatial model, we get a pretty drastic increase in our R-squared there. Right, so if you were to ask me which model is the best to use, if I'm thinking about this, you know, simply from R-squared, I'll say the quasi-spatial model. However, if we look at our indicators of spatial autocorrelation, we see a significant row parameter for our NDVI down here. So this is implying that indicating that there is some amount of spatial autocorrelation and that we probably want to use a spatial model. All right. Conclusions. So our results confirmed findings of local studies and regional studies, which found loss of healthy vegetation near the Afar Depression, so up in the north, and we saw localized areas of increasing NDVI over in Northwest and in the Gambela region. And so these are findings that others have come up with based on their work, but one of the biggest, I think, novelties of this work is the scale at which it was completed. So a lot of the research is done at a small scale, a local scale, or at a regional scale, so including multiple countries in East Africa. And this does not necessarily lend itself to facilitating adequate policy at the national level. And when we're thinking of environmental policy, this is often made at the federal level. And so what we need is consistency across an entire country, right? The national scale is what we need for that. And it's a scale that not much of the literature is focused on. Moving into the conclusions regarding the regression results, again, these are similar to previous studies. Rainfall and NDVI showing a positive and I will say though, temperature in NDVI is a bit more murky. So the results in different studies can differ. And of course, this depends on, again, the region in Ethiopia that you're working in. If you're working at a local scale, this could cause a difference, and season can also cause a difference. And then we see some folks have looked at phases of global climate oscillation and have found that this is also going to make a difference. Now, unlike the previous studies, what this work found is that temperature returned a larger beta coefficient than rainfall. And this is important to Ethiopia, given that we are already seeing a rise in the temperature there. So this could have some implications. Now, I want to point out the regression results in a little more detail. So like I said, they did show some influence from omitted variable bias when we don't consider a spatial parameter. And so this is because of geographic characteristics that are unique to each observation, things like elevation, and that are also correlated with both climate and vegetation, right? So these unobserved variables that are correlated with our dependent and our independent variables that are not considered when we're using a non-spatial model. So in Ethiopia, there's a general positive relationship between elevation and rainfall, negative relationship with elevation and temperature, and this is influencing our biomass, our dependent variable. So this is creating an overestimation and an underestimation of our rainfall and our temperature when we're using that non-spatial model. Now, this has led me to another question, which is, can spatial fixed effects be used to account for spillover effects, assuming that the spillover effects are staying constant over time? That's sort of, I think, where I left off with this paper. Certainly, this paper is giving me more questions than what I went in with. And I will take a drink before I move on to the next one. Wait, what time is it? The clock's broken. That's not very helpful.
It's 3:30, but you have tons of time. You're doing great.
Okay, moving on to the second paper then. This paper is currently under review at Ecology and Society for a special issue on land acquisitions, well-being, and environment. The title of this work is Climate Change, Degradation, and Land Acquisitions, Evaluating Inequalities among competing interests for suitable cropland in Ethiopia. So this paper, again, is drawing a lot on this knowledge that Ethiopia is experiencing a lot of land degradation, and this is expected to worsen with climate change. As we get more extreme rainfall, we get more drought. This is going to alter characteristics of things like soil and soil erosion, potentially and likely leading to more degradation. And this will in turn impact the agricultural production, which, as I mentioned, is a pretty important factor for Ethiopia, given that 72% of the population is involved in agriculture. So land has remained this important factor, for the agricultural sector, but for Ethiopia in general, because of that economic influence and the employment that it provides. Historically, Africa or sub-Saharan Africa has been seen as a region that has a lot of available cropland. However, recent studies suggest that there's actually less available cropland in Africa than we previously thought. And so again, in Ethiopia, we see this diminishing cropland. We see this decline in farm sizes and marginal land being put into production. And these issues are compounded by large-scale land acquisitions, or what we sometimes call land grabs. So these private investors leasing land through the Ethiopian government and rather large tracts of land. These land acquisitions have led to displacement of smallholder farmers, as well as other negative consequences, which I'll discuss on the next slide, as these governments lease what they often refer to as marginal land, unused land, wasteland, to these private investors, when in fact, it is oftentimes prime farmland. It's farmland that is located close to markets, close to irrigation sources, and as I'll show you, the suitability is not so bad either. Right, so there's a bit of a discrepancy in terms of the picture that's being painted by the government versus what researchers have actually found. Now, if the assumption of extensive available cropland were true, then perhaps the government could allow this foreign investment without as much concern for the trade-offs between the land acquisitions or the foreign investors and the smallholder farmers. But again, this is not the case. We know that Ethiopia and sub-Saharan Africa in general does not actually have as much available cropland as previously thought. This image down here is showing you what a transaction looks like before and after. So this top image is showing you before. You can see the nice woodland. Of course, this massive ditch with the guard tower was not there before. This is because this land has already been leased. And so this ditch was dug to keep locals off of that land. And this guard tower did have a guard in it with a gun trying to protect that land. If you drive a little bit further down the road, this is it's the same parcel of land. And this is what it's turned into ultimately. And this is a massive monocrop of maize. All right, a little context on land acquisitions in Ethiopia in particular. So Ethiopia has become one of the most targeted countries for land acquisitions. It retains 15% of all land acquisitions in Africa. And in the beginning of this, as this phenomenon was taking shape, the Ethiopian government allotted 3.1 million hectares to the federal land bank, saying that, okay, these are available to foreign investors. Since 2000, there's been about 200 deals, and approximately 1.4 million hectares has been leased. So the government perspective on these land acquisitions is that, again, this is marginal land or wasteland, and that the foreign investment offers a good opportunity to get the capital needed for agricultural growth in the country. It's going to bring technology transfer as these more mechanized, commercialized farms come in and communicate with the local farmers and spread their technology. And we also see promises like infrastructure and employment opportunities. In reality, this has not been the case. So lots of case studies have taken place in lots of different regions throughout sub-Saharan Africa on these land acquisitions. And what we see is that there's a lot of displacement of smallholder farmers and pastoralists. And this thereby increases the food insecurity, which hinders our poverty reduction efforts. And it has also spurred civil unrest. Now, I want to draw your attention to some of the goals of Ethiopia in terms of development and what the government has planned, right? So there is this goal of reaching lower middle income status by 2025. And if you look at the documentation, there is an emphasis on commercialization, industrialization of agriculture. And there is still mention of smallholder farmers, but these are a bit contradictory if you think about this, right? So prior to the most recent growth and development plan in 2016, there was a much larger emphasis on smallholder agriculture, what they called agricultural development-led industrialization. So a lot of effort and investment went into rural development by focusing on the smallholder farmers and making sure that they could produce to feed themselves, but also, of course, increase the production and fill gaps in their yields. Now, this is important because it extremely successful. The ADLI, the agricultural-led development was very successful. As I said, Ethiopia's economy has grown a lot. And it's this new policy of focusing on commercialization kind of flies in the face of that previous strategy, which was to focus on the smallholders, right? So, reading this, I just think why mess with success? It's going to be important for the smallholders to retain productive land if Ethiopia is going to continue on this trajectory of economic growth. I will point out too, as I get a sip of water, so this is an image of some of the results of the civil unrest. These are two trucks that are owned by investors, that were owned by investors to transport the crops. So the community, with their backlash, resulted in the tipping and burning of these trucks. So it is serious civil unrest that we're seeing associated with these transactions or acquisitions. Okay, so to the research questions now. Again, this paper has 2 research questions, and I'll kind of break them up in parts. The first question, are there disparities in the agricultural suitability of land that has been given to large-scale land acquisitions versus what remains available to the smallholders? Again, trying to get at that idea of, all right, the government is saying that it's marginal or wasteland, but is it really? And then the second question, how does long-term suitability and the potential for climate-induced degradation differ between land within the transactions and acquisitions versus the land adjacent in the Western farming system, where hypothetically our farmers are still going to be able to produce their crops? These images down here give you a bit of an idea. So here's a very traditional farming strategy. Our oxen plow still used very widely across Ethiopia. This image here is giving you a bird's eye view of a transaction. And so outlined in the white is the transaction. And then next to this, you can see all of this small scale farming. So quite a different landscape. All right, now to get at these questions, I use 3 different data sources. The first is crop suitability. This comes from FAO and IOSA, the Global Agroecological Zone Database. And so they determine crop suitability using a lot of different inputs. So things like land resources, of course, land cover, biomass and yield, agroclimatic conditions, and agroedaphic constraints. So soil, ability to work the soil. The suitability is pulled for the most common smallholder crops. And in this case, we are using maize, sorghum, and beans for Ethiopia, which apart from those being the ones most mentioned in the literature, we also use surveys to verify this. So these surveys were taken as part of a larger study funded by NSF looking at land acquisitions in Ethiopia. And you can see here, based on these numbers, that beans, maize, and sorghum were the most important crops for smallholders, both for commercial and subsistence. So we're pulling crop suitability for these 3 crops. And the suitability is based on 3 different time periods. The first one is our baseline. So this is coming from the climate data from 1961 to 1990 using CREW, our climate research unit. And then I also pull the crop suitability for future periods. So for 2050 and for 2080. And these future periods are based on the Hadley Center coupled general circulation model under the A1FI scenario, which is similar to the 8.5, the pathway that are now used instead of our SRES. Now, so this is really the meat of this analysis. This is where the good information is coming from, but it wouldn't be possible without these 2 data sets as well. So the first one is our federal land bank data set. This is showing us parcels of land acquisitions. So what are the boundaries of these land acquisitions? What is the size of them? And this is not easy data to get. This is one of the biggest problems with studying land acquisitions, is that governments don't really want to be transparent about where these are or what land they're getting away. So it was very fortunate that we could access this data. And it came down to 589 plots within the relevant farming systems, which I'll talk about next, for a total of about 5,500 kilometers squared. The farming system is how I sort of determined what crops I'm looking at and narrow down my study region a bit more. So our farming systems are delineated by FAO. They represent regions where farming management is going to be similar, where livelihood pathways are similar, and adaptation as well. So with the farming system, which you can see the farming systems across Ethiopia here, I'm focusing on the maize mix system, this brown area here, and then our agropastoral system above that, and these little white polygons in here are our transactions. And this is also where a lot of the transactions have happened. Most of the transactions are happening, way out here in the west. This is historically where marginalized communities live. So certainly an aspect of inequality or environmental justice to be concerned with there. This is an example of what this data looks like. Again, I pulled it for beans, maize, and sorghum. You can see the suitability class. So suitability is ranging value from 0 to 100, but FAO has also represented it as classes, which you can see here. I should point out, I've reclassified it as others have done, using, putting these categories into 4 categories. But this is the original classification. You can again see our land acquisitions in the red up here and the farming system. And then we have our baseline period, 2050 and 2080. All right, the spatial analysis, spatial analysis really was the method used. Broadly, I can't find a better term for it, so suggestions welcome. But there was some pre-processing to be done with this data set, so it did need to be brought down to 100 meters in terms of pixel resolution. So I believe it was at 1 kilometer, but I'll have to double check that. And then additionally, I needed to mask out areas that, while they're not used for land acquisitions, they still wouldn't necessarily be used for smallholder agriculture, right? They don't have potential there. So things like protected areas where you're not going to find, smallholders, or you shouldn't find smallholders moving in and cultivating the land, permanent water bodies, built land cover, and of course the land acquisitions themselves. So masking out these, we end up with an area in those western farming systems that are still at least hypothetically available to the smallholders. And then spatial analyst tools were used to determine and compare trends across areas of interest. So looking again at the national level and then focusing on the land acquisitions and comparing that to, again, that remaining land in the farming systems that is still available to smallholders. And so in these different regions, I looked at 3 different measures. So the first is just the percent of the land that's within each suitability class. Again, not suitable, marginal, good, and high. And just to get an idea of what is the distribution of the land. I then looked at the proportion of land that is expected to undergo a decline or an increase in suitability class between our baseline period, that 1961 to 1990, versus our future conditions in 2050 and 2080. And so the real change here is that climatological data, from the baseline to the climate models. And so we can say that this is, in a sense, an indication of climate-induced decrease in suitability or climate-induced degradation. And then to get an idea of the magnitude of change in a more spatially explicit manner, I calculate the percent change in suitability at pixels that exhibit a decrease or an increase in suitability. So that's the percent change between the baseline and 2050 and 2080. Jumping into the results then. So first, again, breaking it up, looking at the national level, what you see here is the percentage of Ethiopia's land within each crop suitability class, and you can see the baseline 2050 and 2080. And what we see is that most of the land is classified as marginal suitability. This is followed it is mostly classified as marginal suitability for the production of maize, sorghum, and for beans. And this trend remains consistent with climate change. We see that the percentage of pixels classified as marginal is increasing by 2050 and 2080 as moderate land decreases. Now, in the case of maize and sorghum, some of the increase in the marginal suitability is from improvement that at pixels that were considered not suitable during the baseline. So this does imply that there is some good news. There's going to be some improvement in the suitability at some locations. Now, if we compare looking at this graph down here, this is the percent of area that's exhibiting change in the suitability class. So we have no change. This is areas where the pixel did not jump to either above or below into a different class. We have a decline in suitability class or an increase in suitability class. Now, compared to the baseline, the greatest change in suitability is experienced in sorghum, followed by maize, and then beans, which you can see through these numbers. However, if we account for the pixels that had an increase in suitability, so sort of looking at more of this net decline, we see that sorghum is actually going to be the least impacted because it has the most amount of increase in suitability. And again, it's going to experience those increased or those improved agricological conditions for production. And so then if we account more for that net decline, we see that maize is actually going to be the most impacted by 2080 in terms of the amount of land that is decreasing in suitability. And this map here is showing you the distribution of the change and giving you an idea of the magnitude of change as well. So we have in blue are pixels where the suitability is improving. Red is where suitability is declining. And you can see this top row is 2050, the bottom row is 2080. And we have the first column is maize and then sorghum and beans. So just to give you a nice spatial representation of what this looks like. And certainly some areas pop out, especially down here in the southern highlands, in particular for sorghum, but maize as well. All right, moving on then to looking more at the comparison between the farming system and the land acquisitions, which to me is the most interesting part here. For both the farming system and the land acquisition, pixels are classified, most pixels are classified as moderate suitability, followed by marginal and good. And so you can see that here. It should be most are classified as marginal suitability, followed by moderate and good. So we can see that here. Here we're looking at the farming systems in this second column, and then the land acquisitions in the third column, and of course for maize, sorghum, and beans. Now, what I do want to point out here is that what we see with the land acquisitions compared to our farming system is that there's more land that's classified as good quality land compared to what we see in the land that remains to the smallholder farmers. You can also see that there is a more rapid increase to marginal suitability in the farming system compared to what we see in the land acquisitions, which of course, right, we're starting with more good land, so there's going to be a discrepancy there. But this is a concern because that means that we have in our smallholder regions these farmers that really don't have the capital or the means to farm degraded land. This is what they're ending up with, more degraded land than what they would have if they were still able to farm where the land acquisitions now are. Moving on to the bottom graph here, then looking at the change, the farming system is showing consistently higher proportions of land with a net decline in suitability class, while the land acquisitions are showing more stable conditions in suitability. So again, you can see that here looking at the farming system versus the land acquisitions. If we look at pixels that had no change in the suitability class, you can see that's consistently higher in our land acquisitions versus what's in our farming systems. You can also see that pixels with a decline in suitability class are going to be higher in the farming system than compared to the land acquisitions in all cases. And if we look at the percentage of the net decline in suitability and average this across all the crops, what we see is that 11%, there's an 11% decrease by 2050 and 30% by 2080 in the land in terms of the amount of land remaining to the smallholders, versus 4% by 2050 for the land acquisitions and 25% by 2080. So there is this discrepancy in terms of how the land suitability is decreasing, and we see that it's working in the favor of land acquisitions, not in the favor of the smallholders. So top map here is identical to the one you saw on the previous slide. So again, we have maize, sorghum, beans for 2050 and for 2080. Our blue is showing us increased suitability and our red is showing us decreased. Now, one thing that sticks out in terms of the farming system is just how impacted the bean production could be up in the northern part of this farming system. You see all of that red color showing up here, and less so with the sorghum and the maize. Now, of course, I want to show you guys what's going on with the land acquisitions. It's a little bit tricky to see. It's a large area with small plots, but you can get a sense of what's going on in the land acquisitions down here, and you can see that there's not as much change occurring. Now, the spatial look is nice, but I wanted to try to summarize this in a way that made it a little bit more easy to digest. And so what you're looking at here is the quantiles of the percent change. So trying to get at the magnitude of change. And I'll point out that in a lot of cases here, right, for our maize by 2080 compared to the baseline, and as well as for 2050, and same for beans, we see that there is a larger, in terms of the median, it is higher for the farming system in terms of how much improvement are we seeing. But what I also want to point out is that in all cases across all crops, when you compare the baseline to the future time periods, there is a higher amount of declining suitability or a greater magnitude of change in terms of the decline in suitability for the smallholders. And it's really not enough to outweigh, the positive change is not enough to outweigh this negative change. Now, in terms of conclusions for this paper, again, not surprisingly, private investors have been provided higher quality land for cultivation based on the proportion of land that is classified as, again, not suitable, marginal, good, or good or high. So we saw a lot more in that good category for the land acquisitions, meaning that upfront they are getting better land than what's being left to the smallholders. So that inequality is then resulting in an upward trend in moderate suitability of land in the large-scale land acquisitions, while our smallholders are getting this larger decrease or this more rapid decrease to really non-productive land. And we see large-scale land acquisitions are less vulnerable to degradation, like the climate change indicated by that the ratio of land that's seeing no change in suitability class versus an increase or a decrease in suitability class. Now, as I mentioned before, this has implications for adaptation. So smallholders being left with this lower quality cropland means that they likely will have to have more adaptation and more, more capital to invest to try to, not just cover the yield gaps that they currently are dealing with, but cover yield gaps that are expected to come with climate change. Now, in terms of future work, certainly more detailed analysis is needed to understand what is going on. In this case in particular, I think it's really necessary to look at a small scale and try to understand what these farmers are doing to adapt to climate change. How are they being impacted? What are their livelihood diversification strategies, if there are any, or are they still relying on maize, beans, and sorghum, or are they switching, to other crops? I don't know what time it is.
Oh. You've got like 5 minutes.
Okay, 3:50. Oh my gosh. Okay. Okay, I won't go in much detail about this. So this is the third chapter of my dissertation, something I'm working on now. Working title, An Evaluation of Church Forests in the Landscape Mosaic of Northwest Ethiopia. Certainly not where I expected to end up with my third chapter, but here we are. So background on this, there's increasing pressure on Ethiopia's church forests, and these church forests constitute some of the only remaining forests in Ethiopia. As you saw in that first slide, with one of the first slides with the land cover, a lot of the forest is in the southwest. All right, so there's not much forest across Ethiopia, and the church forests in particular are really biological and spiritual sanctuaries on the landscape. So obviously, with the religious importance, there's cultural significance there. But if we're looking at the landscape, and you can see in this picture up on the top right here, this is the church forest, this cluster of trees, and around it is a lot of savanna, or more likely what it looks like is agriculture. And so if we're thinking about this, the landscape mosaic and the ecology of the larger landscape, these are critical to maintaining biodiversity and also maintaining the functioning of the system, of this landscape within our system, right? So the changes that we see taking place on the landscape, which is really the intensified use of land surrounding the church forests, it's causing issues, and it's something that needs to be monitored for the health of the forest, but also within the larger landscape. And so what I intend to do is to look at how land use intensity is altering ecological characteristics of the church forest, specifically in northwestern Ethiopia. And you can see the study region here. All of these little dots are church forests, which there are 44. And if we do a zoom in there, you can see them a little bit more clearly. So this data is collected by a colleague over in SNRE who went out and surveyed these 44 church forests, and she got ecological data, including variables like the percent of human disturbance, so how much human disturbance has taken place in these individual church forests, things like species abundance and species richness. Now, I intend to also use, of course, our geospatial data sets, things like land cover, which we have for Ethiopia at 30-meter resolution, which is a very nice resolution to have at the national level. Of course, climate and things like precipitation, temperature, wind speed, evaporation, agroecological zone. These are all things that will need to be considered and likely need to be controlled for across the different locations. And then in terms of getting at the land use intensity, I have run the land cover classification, trying to pick out the difference between smallholder farming and intensive farming, as I think many people in the field of remote sensing are trying to do right now and finding that it's very, very difficult. So I turned to some other data sets. So what you can see here is an idea of irrigation versus non-irrigated cropland. This is coming from the International Water Management Institute, which they just put it out, I think, a year ago or so, which was very convenient timing for me. And then I'm also expecting to pull on the Global Agroecological Zone database again, which also just got updated again, very convenient timing for me. And so with the GAEZ, I'll be looking at production volume, which is measured for the most important crop in a given region. All right. Bringing this all, I'm sure I'm past 5 minutes, and I'm very sorry. All right. So this work is utilizing geospatial techniques to examine various aspects of global environmental change in Ethiopia, looking at analyses in a multi-scalar manner, looking at pixel to regional scale to obtain these spatially explicit information, and uses leading edge techniques. So the results of this analysis are providing insights into the links between climate and land systems and agricultural land use. And I'm also trying to consider issues things like structural transformation and environmental justice. Again, tapping into my human geography side, it's there, I know it, I just need to work on it a bit. And then future work will certainly be further investigation into the spatial models and landscape phenomenon that are generated by interactions between social and environmental processes, specifically looking at agricultural activity and environmental change. With that, thank you all very much, and especially thanks to Dr. Southworth, Pete Whalen, Tim Fick, Brian Child, and Cheryl Palm, who's over in AgriBio. Thank you.
Okay, any questions from anyone in the room first?
Do we know where that food that is now being grown, like in the monocultures, that is the maize, just for one example, do we know where that food is ending up? Is that getting exported out of the country? Is that back in the local community? What's happening?
Great question. So I think that the data, like all of the data around the land grabs, it's not very transparent. Certainly what I've heard most, and Audrey or Jane might jump in on this if you have a different opinion, is that it's getting exported, which is of course contradictory to the expectation that land grabs will increase food security in a region because it'll be more productive agriculture, but it's not, because it's just directly being exported back to the country of the investor or highest bidder.
Any questions from anyone online? at that, you stunned them all to silence.
I'll ask a few questions. So who are these land grabbers? So what do you know about, like, what nationality or any details?
I mean, certainly a wide variety of countries, and oftentimes it's more developed countries. China has been a big player, India's been a big player, US has, some European countries. But there are instances where it is domestic, and oftentimes we see domestic and international partners working together as well.
And what can you say about the soils? Like, you spend a lot of emphasis on the climate and the vegetation, but not so much on the soils and the gullies and those kinds of things,
Yeah.
which are certainly elements of land degradation.
Yeah, I don't know much about the soils in Ethiopia. Certainly, maybe not as much as I would like to know. I know that the nutrient mining is a problem because of the lack of inputs going in for the agriculture, and I know that the soils are more suitable in the highlands where that agriculture is taking place. But I think that's about the extent of my knowledge in Ethiopia. Yeah, soils are. I love soils, but certainly not my expertise.
I'll ask a question, a detailed question. In your first paper, you showed the trends of land degradation. It looked like the Afar Depression was the only place that was degrading in all seasons. What's going on there?
I didn't even notice that actually. I'm taking that, so I can't flip back to that. I started that paper when I first started my PhD. It took a long time. And I remember talking to Pete about that, and we discussed that what it's possible is that the change in elevation and that slope could be accelerating the degradation, but certainly there's also a lot of grazing going on up in the north, and so that overgrazing is
Is
causing.
there any agriculture in the depression?
In the depression?
Other than grazing?
I have scoured that area for
Is it-
trading samples
yeah,
and
is-
Google Earth, and there's minimal. I mean, there is some, but really minimal agriculture.
Yeah.
And CRB.
I have a question.
Go, Tim.
Yeah, hi. Carly, did you get a chance to do some diagnostics, perhaps on your residuals from your regression models and see, compare them and see where the model's doing well or where it's not doing well? And, because sometimes much can be gleaned from analysis of not necessarily the coefficients of the model, which you did a good job doing, by the way, and I really enjoyed that. But what I'm saying, sometimes a lot can be gleaned from the residuals. So have you spent time looking at those?
I haven't looked at the residuals, but it is something that I'm interested in, especially because it seems like residual analysis is a way that people are beginning to pick out the effect from human processes, the effect on the landscape from human processes versus climate. And so again, that paper really landed me with a lot more questions than I went in with, and certainly looking at residual analysis to try to understand the climate impact versus the human impact is something I'm interested in looking at further.
Okay, that sounds good. Excellent.
Thank you.
Tim, when you ask a question, everyone, like every student in the room is like, oh my God, no, a Tim question. You're their biggest stressor.
I apologize for that.
It's good. It's good that you do it.
Oh, be proud of it.
Embrace it.
All right.
Anything else? Anything else online?
Kudos.
Okay, well, thank you very much, everyone online, and we will see everyone next week for Akil, I believe, is our next speaker, so another PhD student. So let's have a good attendance for that one as well. And I will see everyone next week. Thank you very much. Thank you, Carly.
Great job, Carly.
Remember, give your sheets to Josh.
Yes.
I think Tim asked me the same question, the exact same question.